So now you've learned that the angular momentum of a point mass can be calculated by taking a vector cross product between a lever arm and a linear momentum vector, which means in magnitude the angular momentum of a point mass is mv times r perpendicular. In the last video you found the angular momentum for a rigid body is equal to I omega. And in that video I had referenced merry-go-rounds as an example of a rigid body, and you might want to do your own experiments in conservation of angular momentum, but the problem is these merry-go-rounds are hard to find these days. The last one I know of in Orange County is on Lido Island in Newport Harbor. If you know of any others, please let me know. So here's the outline of Lido Island. So if you drive up Pacific Coast Highway and start to head down the Balboa Peninsula, before you get too far down you can make a turn and go down Lido Island, and somewhere around here on Lido Island along the waterfront is this park. So here's a close-up picture, and there's the last merry-go-round that I know of in Orange County. If you want to see some other students who tried their own experiments in angular momentum, you can watch the video that I've saved for this Unit 4.2 titled Motorcycle Merry-Go-Round to see the potential dangers of going too fast. Anyhow, let's get to the topic at hand here. The law of conservation of angular momentum. So an experiment you might want to try if you take that trip to Lido Island would be to run as fast as you can and then jump onto the stationary merry-go-round. Now when you land on here, something must be conserved, and that quantity is angular momentum. Energy, well, total energy will be conserved, but mechanical energy won't be conserved. As you run, you've got kinetic energy. And when you jump on, the whole merry-go-round is going to start to turn, and so your translational kinetic energy will result in some amount of rotational kinetic energy, but there will be less rotational kinetic energy than translational kinetic energy. And the reason is when you jump, as long as you stick, there was some force of friction that gripped and slowed down your linear momentum, and so some of your translational kinetic energy was converted into rotation, but also into some wasted thermal energy. Okay, so let's draw more of a bird's eye view of this kind of situation. So we'll just picture you looking straight down as a point mass. There's your mass, there's your velocity, so you have linear momentum mv, and then here's the merry-go-round you're going to jump on. And there's its center of mass. Its initial angular speed is 0, and so its initial angular momentum is 0. So as far as the whole system is concerned, there is, well, when you jump on board and land here, there is some force of friction between your feet and the surface of the merry-go-round. Now, that force of friction pushes backwards on your feet, but that means your feet push forward on the merry-go-round, and that provides a force along with a lever arm, and that makes for a clockwise torque, which gives a counterclockwise torque, which gives a counterclockwise angular acceleration, which increases the initial angular speed from 0 up to some final value. Well, that torque is internal, the torque is external, I should say, to the merry-go-round by itself, but that torque is internal to the system comprised of you and the merry-go-round. So angular momentum is conserved as long as we satisfy two conditions. whatever system you imagine has to be a closed system. We know what that means, just all of the mass is accounted for and no mass gets in or out of the system. The system also has to be isolated. So when it comes to rotation, an isolated system is one in which there may be internal torques, but the total sum of all external torques is equal to 0. Okay. So how would we state the fact that angular momentum is conserved? That means the total angular momentum for the whole system initially has to equal the total final angular momentum for the whole system. So there's the angular momentum of the person initially plus the angular momentum of the merry-go-round initially. That has to equal, well, once you jump on board, you and the merry-go-round become one object rotating together, so that has to equal the final angular momentum of the whole system. So we treat you running as a point mass, and all of our calculations will be made relative to an axis of rotation at the center of the merry-go-round. So that's our reference point. So let's see. As long as you jump onto the very edge, then there's a value of r perpendicular equal to the radius of the merry-go-round. And so your initial angular momentum is your mass times the initial speed you run with times the radius of the merry-go-round. Okay, and then the initial angular momentum of the merry-go-round we said was 0 because it's sitting there at rest. And then once you jump on board, you and the system comprise a rigid body, and so the final angular momentum is the combination of your rotational inertia multiplied by whatever final angular velocity the system gains. So mv r, we'll say mv naught r, is equal to the rotational inertia of the system times omega. Now what's the rotational inertia of the system? Well, it's twofold. A solid disk has a rotational inertia relative to its center of mass of, right, isn't it 1/2 mr squared? But then you're on board as a point mass, and the rotational inertia of a point mass adds an additional lowercase m, that's your mass, times r squared. So the total rotational inertia of you and the disk together is equal to lowercase m plus 1/2 capital M multiplied by capital R squared. So let's write these steps one more time. Step 1, initial angular momentum equals final angular momentum. Step 2, mv naught r, the initial momentum is all the angular momentum of you as a point mass, equals m plus capital M over 2 quantity times r squared. That's the I in I omega. Okay, and then all that multiplied then, of course, by omega. So let's make up some numbers here. Let's say that this person is running at a reasonable speed of 8 meters per second, and they have a mass of 70 kilograms, and then the whole merry-go-round has a mass of, how about 100, and we'll just make it 100 kilogram, make life easy on ourselves, and we'll say it has a radius of, how about 2 meters. So how fast will it end up rotating once you jump on board? So omega is equal to m v naught r divided by little m plus capital M over 2 times r squared. Let's cancel out one of the r's, and the final angular speed of the system is then V naught over R times the quantity M over M plus capital M over 2. So given the values that we provided as an example, the final angular speed would be equal to 8 meters per second divided by 2 meters times the quantity 70 over 70 plus 100 over 2. Now, when we divide meters by meters, it seems like we just get 1 over seconds, but 1 over seconds dimensionally is really the same thing as radians per second. So we have 4 radians per second multiplied by 70 over, let's see, 100 over 2 gives us 50, and 50 plus 70 gives us 120, and 70 over 120 is the same as 7/12. So we have 4 times 7 divided by 12. That's the same thing as 7 divided by 3, which is the same thing as 2.33 radians per second. Okay, let's take this a little further and see if we were right about loss of energy. Let's see if mechanical energy was conserved or not. So I think your translational kinetic energy ends up becoming the rotational kinetic energy of the system plus some wasted thermal energy. So let's find out at least what fraction of the thermal energy compared to the initial kinetic energy exists. So what do we have? Let's find the initial kinetic energy. That's just the kinetic energy of the person running. After all, before the person jumps on board the merry-go-round, it's at rest, so it has no energy. 1/2 mv squared. 1/2 times 70 times 8 squared. Now what does that calculate out to? 8 squared gives us 64. 64 divided by 2 gives us 32. And 32 times 70 gives us 2,240 joules of initial kinetic energy. So the final kinetic energy is 1/2 I omega squared. Okay, so I is equal to, as we said, mr squared, the rotational inertia of U as a point mass added to the whole system, plus the rotational inertia of the disk itself, or the merry-go-round itself spinning around, which is 1/2 capital M r squared. So we factored out the r squared and called this lowercase m plus capital M over 2 times the quantity r squared. So the rotational inertia of this system is equal to 70 plus 50 times 2 squared, or 120 times 4, which is 480 kilogram meters squared. So the rotational kinetic energy after you've jumped on board is 1/2 I omega squared. So it's 1/2 times 480 times 7/3, or 2.33, right? The answer we found earlier, squared. So we get a final kinetic energy equal to 1,307 joules. So what happened? You had 2,240 joules of kinetic energy as you were running toward the merry-go-round. Then you jump on board, and you and the merry-go-round together move with a system of the kinetic energy of only 1,307 joules. So the energy lost, the Q value, is equal to 2,240 joules minus 1,307 joules, which gives you 933 joules of wasted energy. And so as a percentage, we can say 933 joules compared to the original 2,240 joules times 100% computes to about 42% of the original mechanical energy being converted into wasted thermal energy in this example. Okay, so what's conserved in a problem where something is moving and then sticks to an object that can rotate? This is sort of a form of a perfectly inelastic collision, right? These are two things that are separate that become one after they've collided with one another, but it's a rotational version of a perfectly inelastic collision. And we say that angular momentum is conserved in this example, but we found that mechanical energy was not conserved, and that was due to the non-conservative force of friction that acted when you jumped on board. What about linear momentum? Is linear momentum conserved? Well, as you're running, you have some linear momentum that's the product of mass and velocity. So there's an object that's translating through space, but once you jump on board that merry-go-round, and you and the merry-go-round spin together about this axis of rotation, then the whole system is no longer translating to the left or to the right. The whole system stays in place and just rotates on its own axis. So it looks like momentum was lost. Now, why is that? I thought momentum's supposed to be conserved. Well, momentum is only conserved if a system is closed. Well, this is a closed system. Your mass and the disk mass are all accounted for, both before and after you jump on. Here's the problem. You don't represent an isolated system when it comes to linear momentum. There is a net external force on the whole system. One more time. You're running, you jump on board, and the friction between your feet and the merry-go-round represents an internal force. Okay, well, as long as forces are only internal and not external, it seems like the system should be isolated. But we neglected another force. When you jump on board, there's an interaction between the pole that the whole merry-go-round is mounted on and the merry-go-round itself. In other words, you could try a scaled-down version of this. You could maybe construct your own version of a merry-go-round, maybe take something like a piece of cardboard or a paper plate or a piece of wood, and then I'd suggest you drill a hole through it big enough that you can fit your finger through that hole. Okay? And then, I don't know, you can try this. Maybe you can find somebody to throw a wad of clay or something like that, so the wad of clay lands and sticks here. This might be a challenging demonstration, so maybe we'll just make this a thought experiment. So for sure, there's an internal force of friction that allows the clay to stick to this disc. But if you had your eyes closed, I promise you, you would know the moment that that clay hit the disc, because you would feel it. There'd be a force of interaction between your finger, which is acting as the axle, and the disc that the clay is stuck to. And it's no different in the case of the merry-go-round. There's a force between the pole that the merry-go-round is mounted on and the merry-go-round itself. Now that's an external force. So now wait a minute. Then the system is not isolated. So why in the world should angular momentum has been conserved if the system is not isolated? Well, for a system to be isolated in terms of linear momentum, that means the net external force has to equal 0, and here it's just not the case. There's a net external force of interaction between the axle and the merry-go-round. For a system to be isolated in terms of rotation or angular momentum, it means the net external torque has to equal 0. So let's think about that one. The two forces involved are the force of friction between your feet and the merry-go-round, and the force of interaction between the pole and the merry-go-round. Well, the force of friction is an internal force, so we don't have to worry about that. The force of interaction here is an external force, but here's the key to all this. That external force acts right at the axis of rotation. And so it has a lever arm of 0. So even though it's an external force, it's not a torque-producing force. So it turns out the net torque is 0, and the angular momentum is conserved. So in this example problem, with an object that jumps on board and conserves angular momentum, that's really the only quantity that's conserved. Mechanical energy, not conserved. Momentum, not conserved. Angular momentum, conserved.